you very much.
Yeah, thank you very much for Andrew's next introduction. Also, I should thank him invitation. It's my great honor to be here to give a lecture and give this opportunity to give a presentation of my works in recent years. So today, my topic is design and synthesis of the organic functional materials and their optical electronic applications. As we know, since the industrial revolution, the tremendous consumption of the fossil fuels has led to the climate change and the energy crisis. So the photovoltaic is one of the most effective approaches to addressing this scientific issue. Driven by this motivation, I have mainly focused on the design and synthesis of the organic functional materials and study their application in organic dye-sensitized solar cell and the organic inorganic hybrid perovskite solar cell. So first, let me give an introduction of the dye solar cell, the structure and the work principle. Actually, a typical of the dye solar cell consists of the photoanode and the photocathode, and between there's the transporting material. Normally, for the photoanode is consist of the titanium oxide with the F2 conductive glass on which the photosynthesized dye are adsorbed. For the photocathode is F2 glass conductive substrate was deposited with the nanoplatinum was a conductive polymer, for example, the P dot. Between this is the transporting material. Normally, the transporting material is the electrolyte that consists of the redox potential mediators. That I don't know. Yeah. Sorry. Oh, no, it's okay. Yeah. No, it's okay. It's okay. Yeah. The dye solar cell is the typically ectonic solar cell. Normally, the photons are absorbed by the photosynthesizer to produce the electrolyte. Then the electrolyte subsequently was dissociated at the interface. Then the acetone was transported to the relative photoanode and photocathode by the transfer materials. Then complete the circle, the Foley circle. Actually, dye solar cells are favored because his low cost transparency and bright colors and also the high indoor efficiency. Also, the flexible solar cells are lightweight and foldable and rollable. As just I mentioned, one of the dye solar cell advantage is his color richness. But in the last 20 years, the color has been really studied. So also the highly efficient and stable blue photosynthesizer has not been commercialized yet. In addition, in the last several years, the PCE of the poor conversion of the conversion efficiency of the dye solar cell has been not improved too much. So in recent years, I conducted a series of studies to addressing these two key scientific points. Here you see this is the colorful dye solar cell panels. This is very colorful and impressive, but you can see that there's no blue solar panels because at that time the blue one has not been commercialized yet. The main reason was at that time there's no highly efficient and blue photosynthesizer. So I plan to target this challenging project to think about how to design and synthesize the highly efficient and blue stable dye solar cell. First, I found that the anthracene-based materials can help to achieve a stable OLED. Also, the anthracene has many functional sets. That's why I selected the anthracene was the main unit to hopefully achieve the blue photosynthesizer. First, we should know the principle of the designing the blue dyes, that the dye should absorb the whole visible light while exhibiting relatively less or no absorption in the blue region. Thus, when we get the blue dye. This is the design philosophy of the core of the blue dye. First, the electrolyte donor DMP was achieved by the penetration and modification of the steric space. The side chain allow for soluble target compound, also a bit strong intermolecular pipette stacking, and suppress the charge recombination. First, I introduced the heteroatom to construct a more electron donating core. We call it 2BBT. The DFT calculation revealed that from the anthracene to the DMP, the HUMO level move up a lot. Also, the downshift the LUMO level. Then we get the narrow and gap. Also, the absorption spectra see that from the anthracene to the BBT, it's greatly redshift. Finally, a more rigid and coplanar electronic skeleton BBT2 was constructed. Here we the motivation is to avoid the carbon single bond rotation between the two cell phone. Considering that this rotation will cause the vibration of the excited dye molecules. Thus will decrease the excited lifetime of the dye molecules. That's the efficiency. Finally, we constructed a series of the anthracene-based polycyclic aromatic organic dyes. Based on the core we developed, we use the EBTB as the electron donor, also the anchoring group. At the end, we linked the diaroamine to broad the to force broad the absorption spectral response. It's very exciting to say that the R6 dye almost can absorb the whole photons. The onset of the absorption onset is near 750 nanometer. Well, you can see that there is a weak absorption about the blue region. It's 450 nanometer. So it's very exciting to see that the R6 dissolved in TTF. This explains the vivid blue. Also, the device fabricated with the R6 synthesized the titanium film in junction with the cobalt redox copper or STU. This explains the sapphire. It means a real blue colored DSC is achieved. Also, this is the initial synthetic route to the R0 and R1. This is the optimized synthetic to the R6. You can see that the initial synthetic route to R0 and R1 is quite complicated and has many bad-talks. Also, that's the high views. It's hard to synthesize. The optimized one is quite relatively simple and also easy to purification. It's hopefully to commercialize it's hopefully to be commercialized. Actually, now we can buy it from the Swedish company, Dynamo. Finally, the device based on the blue dye R6 also is exhibit a very high efficiency and is very stable. Next, because our human eye is most sensitive to the green light, so the green semi-transparent DSC are more appealing. Actually, the conventional green dye solar cell is based on the porphyrin green dyes, but he has some drawbacks. Now I have a very good blue dye. I'm thinking if I could do something with the blue dye. Actually, according to the color theory, want the blue plus the yellow to achieve the green dye. So actually, based on this, I acquire a semi-transparent green dye solar cell using the R6 synthesized TiO2 film and the injection with the yellow ionic liquid electrolyte. Also, we can have a wide range of the color tuning through the thickness of the TiO2 film, also the thickness of the electrolyte layer. But if we use the classic red dye 1-3 was where the state of the art dye, porphyrin dye, where to see it, the color is tuning is narrower. Also, compared to the state of the art dye, where to see it devices or new green semi-transparent DSC based on our R6 dye, his efficiency improved 30%. Also, you can see that has a significantly superior stability. This is more important. So just I have printed some works on the first generation iodine-based electrolyte and the second generation copper-based electrolytes. But they have some obvious drawbacks. For example, for the iodine-based solar cell, the VOC is limited to the 0.7 to 0.8 volt, and the maximum efficiency is around 12. But for the cobalt, because he has the cobalt complex has the low reorganization. For the dye regeneration, also the ligands around the hexacoordinate center is very bulky, leading to the mass transport limitation. This is more severe at the bracelet. But the third generation, the copper complex, you can see that he has a more positive redox potential. Also, his reorganization is much lower than these two. So it's ready to achieve the open circuit voltage of 1 volt. So in recent years, I have mainly focused on this copper-based solar cell. The co-sensitization is a very key strategy to improve the performance of the solar cell. The conventional one is use the depth of complementary absorption as the less absorbing layer. Here, we propose that the judicious molecular design can lead to the synergetic effect. That's the heavy UC wet band gap dye and the narrow band gap dye, but it's broader spatial response. According to the thanks to the heavy UC of the one synthesizer and the other heavy current of the other, the co-sensitization post system is more efficient than either of the two dyes. So that's the higher efficiency and stability. So the key is to develop the co-sensitizer with heavy UC in combination with the copper-based electrolyte. Thus, here we design a very simple organic donor acceptor co-sensitizer. It's use the triaroamine as a bulky donor and the benzodiazole and benzoic acid as the anchoring group, also the acceptor. You see, this injection with the copper TMBM complex can achieve very high open circuit current or open circuit VOC is 1.24. This is the record value for the copper-based solar cell. The VOC loss is as low as 130 millivolt with the aggregated factor close to 1. It means this dye can suppress the charge reclamation very well. So it's very promising to be used the co-sensitizer to achieve the very high efficiency solar cell. Thus, we use this dye co-sensitizer with a wide response dye 1 to 3. You can see that the co-sensitization system achieve enhanced VOC, also the here DSC, also excellent fill factor. We achieve the 13.5 PCE for convention efficiency. That time is a record PCE. We also do different electronic and the spectroscopy calculation to see what's the mechanism of our strategy. But we found that the co-sensitization strategy is not always effective. Also, we found that the broader spectral response dye tend to aggregate on the surface of the TL2, thus leading to the quenching of the photoexcited dye molecules. Then decrease the photocurrent, also the VOC, overall the poor convention efficiency. Here we proposed controlling the co-adsorbed dye molecules using the pre-adsorber. Then we can get the more better molecule packing to solve this problem. Here we still use the heavy UC dye co-sensitizer and with a broader special response dye SL9. More importantly, we found that we use the hydroxamic acid small molecule as the pre-adsorber. That's a layer of the BPH molecules pre-adsorbed on the surface of TL2 before the absorption of the dye molecules. Thus, we can get a dense and the ordered molecule. If we don't use the BPH as pre-adsorber, these two dyes repeatedly adsorbed on the surface of TL2. And also, we found that the heavy UC co-sensitizer partially dissolved or replaced by the broader response there. Thus leading to, you can see the relatively less dense and orderly. If we use the pre-adsorber, the key is the dyes have to replace the BPT molecules gradually before his adsorption of the TL2. Also he retard the desorption of the heavy UC co-sensitizer. Finally, we get a more order and dense molecule packing and for efficient charge separation. Finally, we for the fourth time we increase the power conversion efficiency of the dye solar cell beyond the 15% and the standard 4 sunlight. Actually brought out the bottle egg of the efficiency. Before this, the efficiency is around 13%. Also, we know with the repeat of the growth of the Internet of Things, the billions of the new wireless sensors will be installed into the building. Now, the battery is by far the most common source of the power, but they have some drawbacks. So now the indoor photovoltaic are very promising alternative to the batteries. The DSC is dye solar cell is a unique technique. Now to power the e-reader and the headphone and helmet is deployed by the industry. Taking, for example, these companies, since 2020, the Swedish company SG has received 130 million to accelerate the rapid launch of their products. Also, the Ambient Photonics received 48.5 million to build the world's largest US low-light solar cell production factory. So, driven by this, we also fabricated a large area of the 2.8 square centimeter to can get a very high efficiency of 30% and different type of the LEDs and over a wider range of the light intensity. So the last topic is, as we know, during the last decade, the organic and inorganic perovskite solar cell has been the game changer in the photovoltaic field. But how to increase the stability of the perovskite solar cell has been the most challenging, which impedes his real application in the market. One hand, the ionic character of the perovskite, also the hydrophilicity of the commonly used activities of the whole transmitted material, such as the TFSI and the TVP, they are very easily attacked by the moisture, then causes the long-term stability. On the other hand, the defects from the surface and the bulk of the perovskite solar cell not only affect the efficiency, but also limited the long-term durability. So for me, how can I achieve the stable perovskite solar cell while maintaining the high efficiency? I wonder if I can use my expertise on the design and synthesis of the organizational functional materials. So my idea is very simple. I proposed the fluorination strategy. That's I designed two fluorinated small molecules. One is the fluorimethylpyridine, TFP. Also another is the fluorinated aniline salt. For this salt, I expected it will passivate the surface to prevent non-radiative recombination. Also, the strongly hydrophobic fluorinated methyl tail protects the perovskite film from attacked by the moisture, then increase the long-term stability. For this TFP, I expected it will improve the boost. Also his hydrophobic can increase the stability. So overall, I expected these two fluorinated molecules can also give the synergetic effect to increase both the efficiency and stability. So first we use the TFMBI as the surface passivator. First we use the SEM to characterize the surface morphology of the perovskite without and with the TFMBI passivator. You can see that with the TFMBI, there's slightly textural structure on top. It indicates that they form a top of layer of the TFMBI layer on the top of the surface of the perovskite. Then we use the XPS profiling to characterize the elemental distribution and the chemical invariance of the perovskite solar cell. From the experiments revealed that the top layer is estimated to 5 nanometer. Also, for the pristine perovskite without the TFMBI precipitate, there is the clear double oxygen double bond. This is from the interaction between the air or the moisture with the perovskite film. But for the precipitated film, there's disappeared. It means the top layer can effectively protect the perovskite film from being attacked by the perovskite film, by the moisture. Then further, we conducted the TRPL to also to reveal what's the mechanism. You can see that with the precipitator, the slower decay indicates the reduction of the surface charge combination. We further use the PLQY. You can see that the precipitated film has about 13 times higher PLQY than the pristine film. It means the precipitator can suppress non-radiated recombination very well. The VOC loss for the precipitated perovskite film is 119 millivolt, but for the pristine is 989 millivolt. First, we studied the TFP to partially replace the normally commonly used the TBP. This experiment sees that the droplet between the water and the surface of the whole transforming material from increase the TFP. You can see that the angle from 70 degree to the around 100 degree. It means the TFP into the whole transforming solution can substantially increase the hydrophobicity of the film. That's the long-term stability. Finally, we fabricated devices. You can see that the champion device for the TFMBI precipitated perovskite film with the TFP can achieve about 24%. It's significantly output the counterpart. You can see that the VOC is about 60 millivolt higher than the pristine one, which is consistent with the PLQY results analysis. So the work provides an effective approach to achieve high efficiency and stable long-term stability of the perovskite technique. Also remarkably, our universe is universal because we also can use the TFP into another new whole transforming materials. Yeah, so that's all. Thanks for your attendance and listening and any question.